Okay, so first of all, I have to apologize. I'm going to make you guys do a video of, or watch a video of me teaching while I'm gone today. But my daughter's sick, and I have to take the afternoon off to watch her. Um, so I'll try to make this as painless as possible and as quick as possible. I'll also throw this up on Edmodo if I can get to it. It'll take a while to upload, so we'll see. But really, this is more so because I know some of you guys are going to be gone on Friday, and I don't want those of you that miss Friday, to be lost because I'll be gone Monday and Tuesday, and it's easier for me to get this all over at one time, and then we deal with that when I get back on Monday, or I get back on Wednesday. So looking at section 3.8, I'm going to keep it pretty minimal because of the fact that I'm going to be gone, so I'm doing a little less than I expected to do, but I'm sure you'll all be fine. Anyway, 3.8, there's science and economics. We're just going to do the economics portion of it to try to give a little bit of some background or information where you could use this at. When I was at ISU, there was a specific class for business majors in calculus. It was actually a little lower than the regular calculus class, and the purpose of it was to talk about some of these topics. And of course, if you took regular calculus, you didn't have to take the business calculus class, but it was for kids who weren't going to take regular calculus but wanted a business degree. So anyway, the big idea is marginal, which, you know, right there, marginal. So in economics, the term marginal is used to indicate a rate. Thus, marginal cost is the derivative of the cost function, and marginal profit is the derivative of the profit function. Now, what that means for us is it's telling us the rate at which cost is increasing or decreasing, or the rate profit is increasing or decreasing. You want a positive marginal profit. It means you're increasing as you sell items, and you would really like to have a negative marginal cost. That isn't always possible, but that is what you would want in a situation. In general, cost does go up the more you manufacture, which is why at a certain point people stop selling things or stop making them. And you'll hear about layoffs and stuff like that. So you can't just keep producing over and over again, because eventually they're not getting bought or the costs get too much for production. So the first kind of problem we're going to do is just basically looking at something like this, like marginal cost, and then trying to compare it to what it actually costs to make the 50th item. So here's number one. It's from the textbook. There's another good example in the actual book about doing this marginal cost, but I figured I'd do an extra one so you had two to look at. So anyway, the first thing we have is our cost function. So the cost of manufacturing X items is X cubed plus 20X squared plus 90X equals, or plus 15. And we want to find the marginal cost function. So that's the first thing we want to do. Then find the marginal cost at the 50th term, and actually find the real cost of the 50th term and compare them. So marginal cost function is quite simple. It's just the derivative, and this is a polynomial function, so we just get to use the power rule. And I do apologize, my handwriting's even worse in pen than it is in the smartboard marker. So there's our derivative, 3x squared plus 40x plus 90. Now, in order for us to do this, we just set it equal to 0. And what we're really looking for is the minimum of this function. Or we're looking for the 0 because this is going to be hopefully our minimum. I'm sorry, excuse me, I'm not thinking properly. This is the marginal cost function. I don't need to minimize marginal cost. I'm just looking for the cost at the 50th value, at the 50th item. So Mr. Moyer's not thinking straight. All we're going to do now is plug in 50 for x. So sorry about that. So anyway, C prime of 50 is going to be 3 times 50 squared plus 40 times 50 plus 90. If I were to actually try to look at where this derivative equals 0 at, it never does. There is no minimum to the there is no point where this function equals 0. Cost continues to go up as we add more items. So now it's just a matter of doing this in the calculator. So go to the calculator. 3 times 50 squared plus 40 times 50 plus 90. So the 50th item, the marginal cost of the 50th item is $9,590 per item. So when we get to the 50th, we can assume it costs us around $9,590 to produce that item. Now to find the actual cost of the 50th item, what we have to figure out is what's the cost of the first 49 items, because that's what this gives us. It gives us the cost after that many items, not the cost of the 49th or the 50th or whatever, but the cost of making 49 items. So what we're going to do is we're going to find the cost of making 50 items, and then we're going to find the cost of making 49 items and subtract those, and that should be how much the 50th item actually costs to make. So again, I'll need my calculator for this. So I'll have to do cost of 50, which means I'll plug it into this function here. Not the prime, but cost of function. So I can do that on the calculator. Actually, I'm just going to cheat because I'm feeling lazy. Let's put this in y1. So y1 will be x cubed plus 20x squared plus 90x plus 15. So we'll do y1 of 50 and actually I'm going to be even lazier. I don't even care to figure out what the 50th one is going to be. I don't even, or not what the cost for 50. I don't care what it costs for 49. What I'm just going to do in the calculator is have it do the 50th total cost minus the 49th total cost. So I do it all at one time. So again, I know this seems weird. I'm not using this, but this function here doesn't mean the cost of the 50th item. It means the cost to make 50 items. So I'm saying, okay, how much does it cost to make 50 items? How many does it cost to make 49 items? And then subtracting the two of them, and that difference will be how much it actually costs to make the single 50th item, which was $9,421. So it's a little off, but again, this is the rate at which it's costing us to get to the 50th. This is the actual cost of the 50th item. So they should be a little different because one's a rate, one's the actual cost. So the problems in that first like 5 or 6 problems are just like this one. Now the next type of problem that the book covers still deals with the cost function, but if you flip to the next page, it's average cost. Oh, and you know, anytime you need to pause or like that, because I'm trying to go slowly, but it's hard to, and it's just yourself. If you need to, just have the person pause it, you know, and then maybe rewind it. Although rewinding on the computers at school is kind of iffy because the video player does like to mess up. So maybe just pause it, and someone can kind of say what they got for some values. Okay, but another way to do some stuff with calculus with business is to look at average cost. Now this we can minimize. And this is what we would want to minimize. Figure out where's the lowest average cost for us, because that means we're making it most efficiently. So again, the another thing we can analyze is average cost. Now, the way you do average cost is explained here. So let's say it costs us $120 to produce 12 items. Okay. Well, the average cost would be $10 because it'd be $120 divided by the 12 items. So it's $10 per item to make the cost of it. So the formula is basically take your total cost function, divide it by the number of items you're going to actually make. So we had $120. We did 12 items, 120 over 12. Now, and if we can do the derivative of this function, which we can figure out where is this cost guy minimum at. So here's our first problem. We've got a polynomial function. This is c of x. What I want to create first is average, and those of you guys that are in prob know C bar, which means the mean or the average. So C bar of x is the cost function, the total cost function, divided by the number of items, because again, that's what x represents. X is the number of items you're gonna make, and then c of x is the cost to make all those items. Trying to make that stand out a little bit more. So now we'll just do that derivative. It's going to be a quotient, or we could make it a little easier on ourselves. In this case, this is a polynomial over another polynomial, and that's actually what the book does. Is the book splits it up and it puts them all over x. So it says, okay, c bar of x is 0.1 x squared over x plus 3x over x plus 2000 over x. And then what it does is it simplifies that to say, okay, this is 0.1 x plus 3. And then they move this up to the numerator, which is actually going to be nice. I know it might not seem like it, but it's going to. So plus 2000 x to the negative 1. When we go to do our derivative, the 0.1x just becomes 0.1. The 3 drops off. This becomes then plus negative 1 times 2000 x to the negative second when I subtract an exponent. And again, this is going to be really easy for us to solve. So this is the derivative. I can make it minus 2000 x to the negative second if I'd like, but it's the same idea. So 0 equals 0.1 minus 2000 x to the negative second. Now if you're saying, well wait, why did I set c prime of x equal to 0 or c bar prime of x equal to 0? Remember, I want the minimum. So I want the place where the derivative equals 0, and that will give me the minimum value. So I'm really just solving this equation. I don't know if, let's say I move this term over here. So now it's just algebra. Okay, now I'm just doing algebra. So move this term to this side. So 2000 x to the negative second equals 0.1. What I can do is, this is really over x squared. So I can multiply both sides by an x squared to cancel this off. And I get 2000 equals 0.1 x squared. Divide by a 0.1, and I get 20,000 equals x squared. So now I can take the square root of both sides, and I get whatever the square root of 20,000 is. And it technically would be plus or minus, but since we're talking about sales, you can't sell a negative number of items. So it's just going to be the positive or the primary root of that. And so I pull my calculator up real quick. The square root of 20,000 is 141. So about 141 items. Or maybe this could be like thousands of items. We don't know. They didn't give us a context. They're not interested in one. It's just that at 141 items, or 100, let's say maybe it's x is thousands of items, that would be our minimum average cost, whatever 141 represents. Now the next one I want to look at is another problem like this. It's number 9 out of the book. Same exact process, just going to be a little more complicated to do, really just in the solving. And the derivative, I guess, as well, because it's going to require us to do a quotient rule. So here's the function, the cube root of x cubed, or sorry, the square root of x cubed plus 9. How they get this, don't ask me. They know this is their cost function. So c bar of x is, and I'm just going to go ahead and put this to the 1/2 power, just because I know I'm going to have to use this. So it is the cost function of x cubed plus 9 to the 1/2 divided by x. Now we get the fun of doing the quotient rule. I'm going to do the quotient rule for a reason. I'll show you why. I know some people, like Mindy Luca, will decide to do the product rule by pulling this up to the top, but in this case it's going to make it easier to do the algebra if we do all the algebra out. Spoiler alert, you could just do the derivative on the calculator, look for where it crosses the x-axis at, and that would give you your 0. But let's just say we didn't have such a tool as the calculator and had to do this by hand. First of all, the derivative of the numerator, we're going to call this f of x, call this guy g of x. The derivative of the numerator, f prime of x, is going to be 1/2. Okay, leave the inside alone. Subtract 1 from the exponent, so negative 1/2. And then multiply by the derivative of the inside using the chain rule. Well, that's just 3x squared. G of x has a very easy derivative. G prime of x is simply 1. Okay. And so now we're able to just plug this into our quotient rule. So C bar prime of x is going to be this guy times x, which there's not really much we can do. It's just going to be ugly. 1/2 x cubed plus 9 to the negative 1/2 times 3x squared times x minus this times the derivative of the bottom, which is 1, so times the 1, and then over the bottom squared, okay, which is x squared. Now the reason I want to actually use the quotient rule here and not the product rule is I want this to equal 0. Well, the only way this guy is going to equal 0 is if the whole numerator equals 0. So I can ignore the denominator and just basically look at this equation here. 0 equals 1/2 times the quantity x cubed plus 9 to the negative 1/2. I'm going to multiply those two together. 3x squared times x is going to be 3x cubed. And then the 1, ignore it. X cubed plus 9 to the 1/2 power. So this is the equation we're going to solve. Now, again, you could throw this in the calculator, look for it to cross the x-axis, and that's where it's going to be a 0 at. See if I can focus this real quick. It's kind of getting blurry, isn't it? I didn't do much, sorry. So anyway, we could do all that, but here's a little solving trick for you. First, let's double everything. I'm going to multiply everything by a 2, and the reason is I want to get rid of that 1/2. So gone. That doesn't matter on the left. It's still just 0. And that gives me then 3x cubed times x cubed plus 9 to the negative 1/2 minus 2 times x cubed plus 9 to the 1/2. Now, the problem with this is this guy right here actually. He's an issue because he's a negative exponent. Another advanced solving technique is you can multiply everything by this guy and it'll cancel them off, but if I use the positive exponent. So if I multiply everything by, again, the left hand side doesn't matter, but if I do x cubed plus 9 to the 1/2 times this, it still just stays 0 on the left. If I multiply this guy, and I'm just going to squeeze it in here, multiply this guy by this to the 1/2, these are the same bases, x cubed plus 9, x cubed plus 9. Negative 1/2 is the exponent, positive 1/2 is the exponent. So you add the exponents, negative 1/2 plus 1/2 is 0. Anything to the 0 power is 1. Boom, he's gone. So I've gotten rid of that. And you might say, well, why would you do that? Well, the problem is set up to work out this way nicely. When I multiply this guy, x cubed plus 9 to the 1/2 to this term here, or this part here, hey, 1/2 plus 1/2, because they're the same base, is to the first power, and I can think of this guy as being gone. So what I actually end up getting is a really nice, easy equation to solve by hand. It doesn't seem like it should be, but it is. I get 0 equals, this member's gone, 3x cubed, minus 2 times this to the first power, so x cubed minus, plus 9. And then I distribute the negative 2. I get 0 equals 3x cubed minus 2x cubed minus 18. And then I get 0 equals x cubed minus 18. And now I'm running out of space. I'm just going to sneak it over here. Move the 18 over to the opposite side. 18 equals x cubed. Take the cube root to solve. That's the exact answer. If you want an approximate answer, you can throw in your graphing calculator. I would do this to the 1/3 power on the calculator. Again, I don't know why it's not so blurry today. 18 to the 1/3. Or there is the cube root button, but I just prefer to not have to go to a menu. So 2.62 or something, or 2.6 items, which doesn't make sense. So, and again, the context doesn't matter here, it's just the work. Okay. Now the last problem we're going to look at on that sheet I've got for you Last problem. Okay. Uh, and this is like number 6 in the book that you're gonna have to do. So pay attention, I guess. Or if you're confused, be prepared to come in Friday morning. And I will say this too, for those of you guys that are gonna be gone, I know Friday, you'll get done about 2 or 2:30. I'll be around after school, so you can come in after school and see me too if you're stuck on the problems from the homework, because I know you won't have time before school because you got to get to the junior, you got to get to Mount Zion grade. So I will be around after school because again I won't be there Monday. But Mr. Moyer loves cookies that his mother bakes, and that's true. I like her cookies; they're very good. And he has convinced her to sell them on Saturdays at a farmer's market. After the first 2 weekends, she has written down what her sales were. On the first Saturday, she sold 200 cookies at $1.25 per cookie, and she had too many left over. So she decided to sell them for $1 per cookie the next weekend. Oh, I left one thing out here. When she did that, she sold 300 cookies. I'll correct yours. Mine is wrong. So she sold 300 cookies at $1 per cookie. So she sold more. Now, we can actually use this information to try to figure out what's the best price to sell the most cookies. Not necessarily the best price to sell all the cookies, or to make the most amount of profit, but just the most cookies. So anyway, in this case, what we have to do is we have to assume that the information here is linear. Now, in real life, companies would do this. They might have more complex models. Maybe it's quadratic, maybe it's exponential or something. But they have, they get a lot of data, and they would set up a model for this. So for us, the best we have is linear approximation. So what we're going to say is our cost per cookie, that's the x. Because we want to know, depending on what our cost is, how many cookies would we sell. So at $1.25 per cookie, she sold 200 cookies. At $1 per cookie, she sold 300. And again, your sheet says 300, mine doesn't, so I had to write it in here. So what we do is we do our slope, which if we do our slope, we get 300 minus 200 is 100. 1 minus 1.25 is negative 0.25. Negative 400. So there's the slope. Okay. And then pick one of them, let's say this one, and write the equation of a line. Y equals negative 400x plus b. Plug in 1 for x, plug in 300 for y. So 300 equals negative 400 times 1 plus b. That's just be negative 400, move it over. 700 equals b. Okay. So now our equation of y equals negative 400x plus 700 gives us an approximation for given any price, because again, remember, x is the price of cookie. Y equals number sold. Okay. If I pick a price point, how many I can expect to sell. So let's just say I decided, all right, I liked $1.25. I liked $1, but let's go 50 cents a cookie. Okay. Let's say I decide to sell them 50 cents a cookie. So negative 400 times 0.5. 0 for the cost is 50 cents plus 700. She could sell 500 cookies then. Okay. Now what we'd like to look at, okay, is the fact of, is that the best price based upon this information? And what that means is we might not be able to really sell 500 cookies. I mean, if I can't imagine that, okay, I will sell them for 10 cents a piece or 1 cent. Well, it's kind of unrealistic to imagine that forever it would perfectly work that way. At 1 cent per cookie, we're saying we're going to sell, I don't know, what is this? 696 cookies. Well, if I sell them for 1 cent per cookie, we'd have to imagine we're going to sell more than that. If you sell it for 1 cent per cookie, we might sell 5,000 or something. So this model only works over a certain amount of time. So what we can actually set up, though, is a bit of a profit equation for this. And what the profit equation would be is profit equals number sold times price. Okay. Well, for us, that means really X times Y. Or really, yeah, number sold, which is Y, times the price of the cookie, which is X. Well, what is our number sold? Negative 400X plus 700. Okay. So, yeah, so profit, or sorry, not profit, this is revenue. Profit's what you make after you've done revenue and cost. Sorry, we'll talk about that on Friday. So revenue is number sold times the price. So what we're looking for is what's the best price to sell the most and kind of work that out. So we have, we'll call it R of X equals number sold, which is negative 400X plus 700 times X. Now, what I have to do then is simplify this. Don't want to do the, don't want to work this out with, two iterative values. So we'll have negative 400x squared plus 700x, and then we'll take our derivative. So negative 800x plus 700. Now the question is, when is this equal to 0? Okay. Well, 0 equals negative 800x plus 700. Move the 800 over. 800x equals 700. Divide by 800. We get x equals 7/8. Or what that really is 0.875. So if we want to max out our numbers sold revenue wise, we would need to sell them for 87.5 cents per cookie. Now that's not possible. So what we'd probably have to do is sell, like, I don't know, sell the cookies for, say, if we double that, the 0.875 times 2 I think is $1.50. Just make sure. No. Wait, 0.875. I don't feel like doing the arithmetic in my head. It's too late. It's $1.75. So you could sell like 2 cookies for $1.75. Or you could double it again and do 4 cookies for $3.50. So, you wouldn't do it for that, but now you could say, okay, and people probably might say, I'll buy more because they think I'm getting a deal. 2 cookies for $1.75. So that's what we're saying is our best value. Now, the next thing we could do with that information then is, once we know that, we could say, okay, well, what do we expect to make money-wise? What do we expect our value to be for, or at least our number of cookies to sell? So our formula for that was y equals negative 400x plus 700. Okay. Well, we know that we want to charge 7/8 or 0.875 plus 700. So throw that into the calculator. Negative 400 times 0.875. So, oops, sorry, plus 700. I forgot to add the 700 there. So now we'd say, okay, if I sell them for 87.5 cents or $0.875, however you want to think of it, I should expect to sell 350 cookies. And now I could then kind of reasonably say, okay, that's, there's my amount to make for my next weekend. Now, I want to stop you here because I do want to give you some time to work in class. Plus, if you need to go back to something, you can do that. But we're going to take this problem and extend it in class tomorrow and look at some other things that happen with it. So, if there's anything you don't understand, come in Friday morning if you can. If you're going to the prob fair, stop in after school on Friday. It might just take us 5 or 10 minutes to kind of go through that. I apologize again for being gone and making you do this, but I really wanted to hit this primarily while the people that were at the prob fair were in class. I know it's like only 7 or 8 people, but still, I'm gonna be gone Monday and Tuesday, so I don't miss that. And yeah, if you have any questions, I don't know, shoot me an email or something like that. I'll do the best I can to answer while I'm gone. So hopefully you're not too hungry, and hopefully you enjoy your 10 or 15 minutes you got in class still. All right, thanks.